we're moving to a group who worked a bit more on like river processes and flooding, and so we're like slowly making our way downstream.
Is this thing working? Okay, cool. Okay, so we are the channel evolution as a function of water, formerly known as the flood group. We've had many evolutions just past flooding. And so I'm Morgan. I'm going to talk a little bit about the approach that we decided to take, mostly in being, we wanted this to be more of a like exercise of getting introduced to and getting comfortable with importing things and making DEMs and using LandLab as a tool to understand channel evolution. This was a very interesting introduction to this, and so we decided to make it very simple and kind of model it after what we've been shown by our incredible team here during this week, and thankfully been using lots of their notebooks and components to do this. And so starting first with looking at just two LandLab components, priority flood flow router and lateral channel migration, namely the lateral rotor. This part, we decided to focus more so on the downloading a real DEM and using open topography and BMI topography to do that. And so you can see here that we're kind of bringing in all the topography using API keys and stuff, which I still don't understand, but that's fine. We'll get there. And getting this really beautiful DEM that's currently in geographic projection and now moving it into a projected coordinate system on which we can import it as a LandLab grid object and run our cool components. The first being the priority flood flow router, which we use the very famous D8 flow algorithm and a bunch of really cool things to get the now DEM and the flood accumulation, visualization of the flood accumulation. And so using that, and now with some sort of flow routing, we can now incorporate the lateral rotor, which is really just telling us the movement of the channel laterally, not in the incision direction. And we basically run this until all of the changes in the lateral erosion component are no longer zero. You could write a for loop for that, and that would be a fun exercise to include. And so this is just a visualization of one component or one of the outputs from this component being the volume of eroded material shown on the grid, formerly DEM, or is the DEM, as well as the sediment influx. And if you wanted to further investigate other things that you could get out of this, we included a way that you could do that using the output var names thing. So just an example of what you could do with that. I'll pass it off to my lab mates.
All right, hello. So the next thing that we wanted to do was to try to incorporate several different components in LandLab into a synthetic grid and try to, see how they work together, and then try to erode some channels on some landscape with some precipitation. The first thing that we have to do is to import our proper packages. So if you scroll up just a little bit. Okay, thank you. So the components we use are Fastscape Eroder, Priority Flood Flow Router, Channel Profiler, and Spatial Precipitation Distribution. Then we had to create our grid. So we wanted to keep it sweet and simple, something small with like 2 main channels. And if you scroll down, we have our nice synthetic topography. So we have a nice little slope with some bumps that will kind of direct the flow on the landscape.
So a landscape is not just going to flow by itself. You're going to have to need some precipitation. So if you scroll down here, we have our initializing the precipitation event. So what this is just a gradient done with a monsoon type storm system, and then you can also change your flux and intensity of the rainfall. And then the second figure we have down here, we have infiltration, which is the water unit flux graph, which is just rain minus the infiltration.
Yeah, so once we had the precipitation and infiltration setup, we wanted to calculate the surface water discharge. And that's why we added the precipitation and infiltration component as well, more like on a dynamic scale. And the surface water discharge is calculated so that we can feed it as an input for our next component, which is a fast-skip eroder. So for this, for calculating the surface water discharge, we use the priority flood flow router. This has been already been talked about from a lot of friends of mine from ESPIn, even my colleagues over here. But to give a brief about it, that it's a component which uses flow accumulator and automatically calculates the surface water discharge at each node. So, and it also handles the depressions in it automatically. So in this step over here, we feed in the topographic elevation as an input to basically identify where the flow is going, kind of flow direction. And the next step was calculating the surface water discharge, which uses the input, the water unit flux, which Lei just talked about it, and calculates the discharge over here. So here is a plot which shows the direction as well as the amount of discharge. So the white or the gray pixels are here basically where there's a higher discharge, and the black areas are where there is no or lesser discharge. So now this will be used as an input in the fast-skip eroder, which Caroline will be talking about.
Hello again. So in order to really see how our channels evolve over time, we use Channel Profiler to plot our initial channels. So we only, again, wanted to focus on 2 main stream channels just to keep it easy. So thank you. So here we have some profiles of the 2 streams and a map down view of our 2 streams. The teal one, pretty long, starts at a high elevation, goes pretty much through our entire watershed, and we have a second smaller purple stream over on the left. So the next thing we have to do is to use a stream power eroder component, which we are using Fast-Skip eroder. It's pretty nice. So in order to see differences in erodibility of the surface, you can change the K value, bigger or smaller, if you want to have a more stable surface or not. And then we also use that surface water discharge component to actually erode the landscape. We decided to plot every 100 years for 1,000 years total, and you can see over time our landscape does evolve and something does show up. If you keep going, yeah, so you can see that the rivers start to become more prominent, so there is more erosion. There are then some tributaries that form off the main channels. So we did it. All right, so the last thing that we wanted to do is to then plot again using Channel Profiler our 2 channels to see how they have changed over time. And initially we can see that that purple channel has definitely changed. Precipitation has caused erosion on the higher elevation areas, which then made a nice little stream channel that connects to the bottom of the purple channel. So that's nice. Also for the profiles, you can see that they've gotten a lot smoother over time, less jagged, less bumpy. So
well, to conclude our group project, our objective was very simple, just to run land lab and play with parameters and component for landscape modeling. We work with fast-skip eroder, which relies on stream power incision model. And by adjusting values for like erodibility coefficient, drainage area, surface, slope, we managed to simulate a realistic catchment process. And over time, our simulation showed that how irregular topography evolved into a structure, a river channel landscape. And we managed to generate like classic concave of longitudinal river profiles. And in the part of like climate, we introduced rainfall as a dynamic parameter. And by providing the rainfall intensity, we assess the sediment flux and lateral variation of channel. So overall, LandLab is effective tool for numerical landscape modeling, and it is very user friendly for researchers from different background and for those who don't have previous experience of numerical modeling. Thank you all.